We'll start in next 4 minutes. Very good afternoon, everyone. We'll start in next 2 minutes. Okay, guys. It's 3 p.m. So we can start today's discussion. So right now we are in the week 4 of Technique of Material Characterization course, and like in this course, in this particular week, in this particular discussion, we are going to talk about whatever has been the concept that has been covered in the week 4, and we'll try to solve few questions based on them. So before I start, I would like to ask you, do you have any doubt or any query regarding the course or any concept that you want to ask me? If yes, please let me know. You can always text in the chat box. Also, you can unmute yourself if you feel free so, and you can interact with me. Okay, since there is no doubt, we can do one thing. We can start with the today's lecture. So let's see the list of the topic that has been covered in this particular week. They are as follows. The first thing we have discussed is about the Monte Carlo simulation. After that, we discussed about the mode of the different mode on the TM. For example, that bright field mode and the dark field mode. And then we discussed in detail about the electron diffraction in TM. Still, the electron diffraction in the TM, the section is not completed yet. So the entire week 5 will be completely based on the electron diffraction. So we have, we to certain extent we have covered it, but still the last fraction is still remaining. So we'll solve questions based on the content that has been already covered. Okay guys, so these are the list of the topic that has been covered in this particular week. Let's start with the Monte Carlo simulation. We'll one by one we'll try to see the concepts. We'll try to just revisit them, which has been already covered in the class. And once we went through them, we'll try to solve a question based on that. Okay, let's start with that. So what is this Monte Carlo simulation we'll talk about? See, you have the specimen, the electron beam is coming. Now we know that it's going to interact with the specimen and it will create certain volume. The interaction volume, like from what region, from how much region the information has been extracted. Okay, so Monte Carlo simulation is more or less will try to give you the information that what is the size, the simulation will give you what is the size of the interaction volume, what is the depth of the interaction. Okay, so those information it will give. One thing to note down, Monte Carlo simulation is work very well for the SEM. Okay, still it's not working. It works very well for the SEM or and usually for the thick specimen. For example, if you are using the thinner specimen, the interaction is only happening till this. So we cannot say that what is the volume of the interaction, right? In that it will be restricted. While if you are allowing the entire beam to interact with the specimen, then it's like, okay, like in the SEM, we know that it happened. While in the TM, it directly passed with the specimen. So Monte Carlo simulation is more or less work very well for the SEMs, for the thicker specimens. Now, so what is happening? Here, let's try to, you and me, we both, all of us, we will together will write few things over here. This is a case one. Let's only consider this particular thing. Let's only consider this two diagram. What is happening that the electron came, interacted with the specimen and it created the volume. It created some interaction. So in the first case, the interaction is this much. In the second case, interaction is larger. Let me tell you, what we are wearing over here is the energy. The energy of the electron beam. With what energy the electron beam is coming. So what do you think? When the energy is more, in that case, the interaction will be larger, or when the energy is less, in that case, interaction will be larger. Considering we are talking about the thick specimen. We are allowing the entire interaction to happen. So, among the case A and B, which one is corresponding to the high energy? Yeah, anyone? Okay, very good. So, yes, Ahmad, yeah. So it's option B. Yeah, Uday. Yes, Sidhu. So the answer is B. Here, the energy is more, so the interaction will be more, right? Now, so first thing we have understand, in here also we can say that the energy is more. From here to here if we go, the energy is more, so the interaction volume is more. Now, let's talk about this too. Here, the variations is about that is Z, the atomic number. The variation is about Z. When you have, for example, the higher Z atom, it means that they will try to interact more with the specimen. Higher Z material, it means that their interaction will be more, and they will try to retard the energy which is provided to them. They will try to retard the energy which is provided to them very in the initial stage only. So what will happen that higher Z atom, having more nucleus and all, so they will interact more. The thing is that their interaction will be quite large in the near section itself, because they will try to absorb all the energy of the electron quite early. So in that case, what we can say that here the interaction is this much. Here the interaction is this much. One will think that no, here the interaction is more, but the thing is that the depth we are not talking about the depth right now. Entire volume we are talking about. So what is happening that more is a z. The material will try to interact more and more. So initially only like they will consume the entire energy of the electron beam, and they will not allow it to pass more. So more Z atom will restrict the more what we can say the depth, the penetration in the depth point of view. So here the depth is more. It is a D1 and D2. We know that D1 is more than D2. The depth is more. Why it is happening that? Because in the second case, this is the D2 case, the interaction, the electron beam, the energy which electron beam has, that energy is being we can say that the consumed for it to go for the interaction, that to initially itself compared to the case 1. So we can say that the higher Z atom will lead to the low depth of penetration. Okay, so here in the second case, in this case, this one is having the low Z, sorry, high Z. This one is having the low Z. Clear? Now here also the same thing. If we try to compare this thing again also, here the depth of penetration is more, here the depth of penetration is less. So again we'll say the same thing, okay, that here this is the higher Z atom compared to this case. Clear? Any doubt in this case, let me know. You will find one question based on this in the assignments, so that's why it's necessary to discuss that. So overall what we will say that the high energy will correspond to the more interaction volume. High energy means the electron beam energy will correspond to the more interaction volume. Higher Z atom, higher Z material will retard, like will more is a Z, less will be the depth of penetration. Clear? Okay, since we are done with this particular thing, in this concept any doubt? Okay, since there is no doubt, let's move to the solving few questions based on this concept. The question number 1. Monte Carlo simulation primarily describe for the electron interaction with the specimen A. Scattering angle, elemental trace present in the specimen, electron trajectory, variable mass thickness. What do you think? What this particular simulation talks about? Very good with that. It's talk about the electron trajectory. How the interaction is going to happen, what will be the depth of penetration, what will be the volume of penetration. Also one thing Monte Carlo simulation talk about that what is the radius of the interaction. Okay, it will give you the radius of the interaction also. So let's with that we have solved the question number 1. So it's talk about the electron trajectory. Okay, what is a Monte Carlo simulation and how it work or done? Monte Carlo simulation is like see, practically what we want to know that in Monte Carlo simulation, first of all, we are passing the electron. Yes, it's a mathematical model. So what it talk about, let's say just now I told you that it's a radius. It will talk about what is the radius of the interaction volume. Okay, so the equation is given as, I have wrote the equation somewhere. Okay, yeah, I will write it here. So the radius of the interaction volume will be given by 27.6 times A divided by Z 0.89 and density multiplied by E naught to the power of 1.67. So this is the entire model which they came up with, where Z is an atomic number. Okay, Z is an atomic number. See, now we can see that more is an atomic number. If Z is more, then R will be less. So here also what we have talked is, the Z is more here. So the radius here is less. Here radius is more, right? So this is what we talk about. Now let's consider another aspect also, E naught. E naught is the incident electron beam, the energy of the electron beam. If E naught is more, then the R will also be more, right? Here we can say that here the R is this, here the R will be more. More is the energy, more is the radius. So it's a mathematical model. What we talk about that, okay, the electron went to the specimen. Now how it is scattering? So more or less what is from what volume of the specimen you are getting the particular information. Let us say this is the specimen and you focused your beam on this particular small region. What it will, you will think that this is the region which is giving you the information, but it's not the correct. Okay, the information is been collected from this entire volume. So you will think that, okay, this is my spatial resolution, but no, this will be the one. So Monte Carlo simulation will more or less will tell you, okay, under if the atomic number is more, then how the volume will change. If the more energy you are going to use, how the volume is change. Let us say in your case you went for the SEB, you don't want to go to high depth. You want to collect information only till the surface. For example, someone did some coating and they don't want their the coating is in the nanoscale, let's say. So they don't want to go to very depth. So in that case, what they will do, they will reduce the energy bin. So by understanding these things, you can create a better, you can generate a better microstructure. Okay. So we'll keep this formula in the mind, the model in the mind. So now let's try to solve the second question based on this. The KO range describe, what does it describe? This, we are talking about this RKO, okay. So this is what it describes. So what does it describe? The wavelength of the emitted X-ray. The hemispherical interaction volume containing 95% of the electron interaction. The resolution limit of the optical microscope. The thickness of the TM specimen. What do you think? Very good. That's option B is the right answer. It's yes, Prela. It's like the option B is the one, and it's more or less we'll talk about the hemispherical interaction volume. Okay, very good. If any doubt, guys, let me know. If not, let's move ahead to the next question. Question number 3. Now this question. In this question, what we can let's have a look. Higher atomic number Z material in the SEM typically exhibit. Atomic number is high. Z is more. What is going to happen? Large interaction volume and more backscattered electron. Small interaction volume and few backscattered electron. No change in the interaction volume. What do you think? See. Yes, very good. I made a mistake in creating the question, so I think I should remove this part. Yes, Prahlad, you are right. Option B is the one, but second part should not be the one. Smaller interaction volume, but yeah, we can say that also the more backscattered electron. Let's not talk about the SCM part of those things, in which case we are getting. So the right answer is option B. Very good, everyone. So this is how it is. because from the simulation we know that second part we know that more is a z, the r will be less. Okay. Okay. Okay, let's talk about the next question, question number 4. Here. Now, the first one, the KO range is precise tool for calculating the TM resolution limit. False, right? Very good. The reason why it is false that it's not a precise tool. It will just give you some rough estimation, but it's not the precise tool to calculate the resolution in the TM. Okay, very good. Second, Monte Carlo simulation ignore the atomic number and accelerating voltage effect. What do you think? Monte Carlo, again, very good, it's a false. We took this thing into account, atomic number and accelerating voltage. KO is applicable for TM? No. No, Prahlad, it's not applicable for TM. Because we need entire volume to interact, while in the case of TM, our specimen thickness is very low. So the Monte Carlo simulation is mostly applicable for the scanning electron microscopy. Okay, very good. C. Higher accelerating voltage in SEM increase the interaction volume. Very good, it's true. The last one. The backscattered electron yield decrease with increasing the atomic number. False, right? I should have put this question here. It should be in the SEM section. Anyway, since we are able to answer it, that's all that's my friend. If any doubt, guys, let me know. If not, let's move to the next question, question number 5. Okay, this is the last question on the Monte Carlo simulation. The KO range depends on, did we already talk about it? No, yeah. The KO range depend upon which one? Atomic number, atomic weight and atomic number only. Atomic number and density only, instant beam energy only. Atomic weight, atomic number, density and instant beam energy. Very good. Yeah, that's right, everyone, because we have saw that with the formula that it depend upon the density, atomic number, atomic weight and the energy of the electron beam. This was the question number 5. Something not got printed seems like. Now, let's move ahead. Now from now onwards, our discussion will be entirely focused on the transmission electron microscopy. So before that, let's have a look. We have the electron gun. We have already talked about this particular gun. After that, we have the condenser lenses, which will condense the electron beam and it will focus onto the specimen. So this is our specimen. Okay. Now, after that, what is happening? This electron beam, it went through the specimen. Now it is going to interact with it. The interaction can be elastic. It can be inelastic also. In majority of the cases, we try to avoid inelastic scattering in the TM. Limiting, that's why we are limiting to the thinner specimen. Now, the interaction is elastic, let's say. So what is happening that the electron beam, it can interact with the electron, since it is elastic, it is going to interact with the nucleus. And so it can change its trajectory. Okay, we know that Rutherford scattering, that if due to the Coulombic force between the nucleus, the positively charged nucleus and the negatively charged electron which is incoming, due to that forces, the electron can change its path. So what is happening that we can say that it's a scattering in some other direction. So if you try to see the direct beam, what will happen? In the case of direct beam, you will see that okay, some certain region, the one which is scattered, it will look to you darker because that the beam is not going to capture. While and the certain region who is not scattering, it will appear to be the bright. So this is the entire thing. One can also say that what about the diffraction? Diffraction is also the one of the kind of the scattering. Okay, it's a special case of the scattering, we can say. So if the diffraction is happening, that again the wave is going to bend, like it's not going to straight. It will not follow this optic, the straight. It will divert from its path. So we are not going to capture in the direct beam image. So in that case also it will create a contrast. And our aim is to see the contrast. The contrast which is generated is the one which is going to tell, okay, if the grain is there, grain boundary is there, different atoms are there, those things we are going to see. Okay. So this was all for the general overview of the TM. If any doubt, guys, let me know. Okay. One thing, how can we detect the image? So we want to form the image, right? So for this we are going to use the fluorescent screen. On this screen, what is happened that if electron will fall onto this, certain reason it's falling more, certain reason it's falling this. We know that fluorescent screen is what? Fluorescent is some material, is the one, like for example ZNS. What it will do, it can absorb the electron, it can go to the high excited state and it will emit then the absorbed energy, right? So this is what is going to do. So the region where the more electrons are coming, that the brightness of that particular region will be higher because the more excitation will happen. This is the fluorescent screen working principle. If certain reason there is no electron or very less electron, the excitation will be less, and like less number of photon will be generated in return, and so our eye will be able to see that that region is comparatively darker with respect to the region which is bright. Okay, so now let's try to answer this question number 6. What is the diffraction electron in SEM and TM? What is diffraction electron? The electrons, the signal which is coming from the diffraction, for example, the diffraction phenomena, we know, like in the case of X-ray also it will diffract, right? And X-ray is also going to diffract provided the condition of the Bragg law is X-ray is okay to me. Okay, so it's if the condition of the Bragg's law is satisfied. The same thing, X-ray is just a wave. Same way, instead of X-ray, let's replace it with the electron. So now what is going to happen, that this electron is again going to, if n lambda equal to 2d sin theta is satisfied. Now instead of X-ray, here we will put the wavelength of the electron beam. So now for this also, the condition is same. The more or less, the principle behind it is same. So in that case, what will happen if the d spacing is going to, d spacing and theta are in that, like at particular theta, since the n lambda is fixed, lambda you fixed, so at particular theta you will get the particular d spacing. It's the same thing. So this is the diffraction which is happening. So now in the case we see that what we have saw that, let's say the electron was the beam was going in this path. After the diffraction, it will divert by the angle of 2 theta if the diffraction happened. So now what is happening that, so this beam which was supposed to go ahead, which we were supposed to see in the bright direct beam, we are not able to see. It's scattered, it's went to somewhere else. So now this is the one which is going to produce the contrast. So now for example, certain grain who are in the orientation where this particular Bragg's law is satisfied. So what will happen? Those grain will diffract. And now those grains, since it is going to diffract, the images, that will not be there in the direct beam. So what we will get in the place of that particular grain, it will be darker. Scattering and diffraction are the same. I would say the if the if the scattering is the entire circle, the diffraction is spatial part of it. In the scattering, the elastic inelastic scattering is also taken into account. Inelastic scattering is the one where the loss of energy is also there. While in the diffraction we know that there is a no loss of energy. It's just a directed. It's diverted to some other location. So it's one of the elastic interaction we can say. The elastic scattering in the case of TM we can say that it's a diffraction. The phenomenon of diffraction we talk in in the terms of the wave, and the elastic and inelastic scattering we talk about in the terms of the considering the wave to be the particle, considering that particular beam to be the particle nature. Okay. So, but more or less one can say that the elastic scattering will be this diffraction will be created because of that, right? So, if the entire thing is scattering, the smaller one is the diffraction. In this, some other scattering will also come like inelastic. The energy loss which is there, like it was told the diffraction spot, that the spot will also be created, right? See, we are going to discuss that part also. Here, see, the diffraction spot is created because of the diffraction is happening, right? So if the diffraction is not happening, n lambda equal to 2d sine theta, yep, then n lambda equal to 2d sine theta will follow. Yep, that's true. So the diffraction is only happening. The diffraction is happening because the particular plane, the particular grain having the orientation of the plane is satisfying the Black's law, and so it's not coming in the direct beam. While if you, let's say this is your diffraction pattern, this is the diffracted beam, so this is the direct beam, remaining on the diffracted beam. If you focus here, let's talk about the grain which is diffracting. Let's say the grain which is diffracting, the diffraction is coming over here. So in the direct beam, if you try to image this particular diffraction, the direct beam spot, in that you will not see that particular grain. You will see that okay, there is a dark is there, like it's a darker color compared to the other one. Now, instead of this, let's say you are doing your imaging using that dark beam condition. Okay, instead of the dark beam, in that case what you will see, if you are that particular grain will appear if you image using this particular diffraction spot, what you will see that particular grain is the grain which is bright in color.
I just have a query.
Yeah,
Am I audible?
yeah, you are able. Please.
Actually, in the class lecture, I have seen diffraction spot. Now, my only point to understand, when professor lecture, it was told diffraction spot. It was not discussed about that whether n lambda sine theta followed or not. First part. Second part, what happened? Suddenly telling scattering, then started telling diffraction spot.
Yep.
So just I need little bit clarity to understand diffraction spot it is telling, because it is transfer electron is passing through the TEM sample, correct?
Yep.
It is a transparent. It is one side to other side it is goes, and once what is the diffraction spot? And with the diffraction spot, nowhere it talk about the n lambda sine theta. So
Yep.
also we are talking about the scattering. Scattering means interaction deflecting his path.
Yep.
Okay. Now, I think I need little bit clarity with respect to this point only. Why it cannot be the scattering spot?
Okay.
Most of the time, Sarah has told scattering, scattering, scattering. Suddenly, it has told diffraction spot. Now, why it was not told as a scattering spot? That is my point to
Okay.
understand.
Got it. Yeah. Yeah. Let me see whether I have that particular image to show you, and I'll explain that part. Okay. I don't have that particular image. Let me check my PPT. Okay. Better I draw. So now, uh, it's very good question, and one should know the clarity what is happening. So let's say this is our specimen. This was the direct beam which was coming in, like the primary electron beam, which is going to interact with our specimen. Now it has interacted. Okay. So now what will happen? What is happened that it will give the direct beam will be there. The different diffracted or we can say scattered beam is there. Okay. So now we are getting all the beams. Now there is a objective lens. Let's say we are drawing the lens like this. Now the series of the lenses, objective lens, projector lens, and those things are there. Now let's say this is the point where you want to image. This is the screen. So now all of them is going to it's going to do. It's going to converge them. Let's say direct beam is coming over here. It will have some focal point. This objective lens will have some focal length. Let's say this is the plane where it is going to converge. So now the direct beam will converge over here. Now the diffracted beam, the beam which has been diffracted far from the lens, far from this particular direction, they will converge somewhere over here. They will converge somewhere over here. So what we are going to do is, what we will get if I try to image only this particular plane, let's say this back focal plane, what I will get the direct beam. I will get the diffracted beam. This will be the diffraction pattern. Okay. So this is the direct beam, and remaining things are the diffraction which is happening from different grain, different planes. Now, using each of these diffracted diffracted spot that we have got, we can image them. So now what is happening that, let's say we converge the beam to a particular point. This particular direct beam we have converged. It interacted and it's converged more or less, and now we are seeing it. Now while we see, we will project it onto the screen. Now this is just going to give us the information. So now you can convert the diffracted spot, the the pattern to the image. But let us say you are the operator and someone came and told you that no, I don't want to see the image, I only want to see the diffraction pattern. What in that case, what you will do? You will strengthen this objective lens in such a way that this focal length will change. Instead of focal length being over here, the focal plane being over here, you will shift the focal plane to your screen. In that case, you will see these particular spots. And if someone told that, okay, no, okay, I've got it, okay, this particular this is the plane which I was interested in, or let's say this is the diffraction spot which I'm interested in. Now I want to see which are those grain which is contributing to this particular diffraction spot, this particular one. So in that case, what you will do, you will try to move that. Okay, what you will do, okay, you will go to that particular spot, let's say for a time being, let's say that spot is somewhere over here, and you will move your aperture in such a way that you are only focusing, you are blocking remaining all the things. So in the TM, you will, whenever you see the diffraction spot now, you will see something like this is also there, which is blocking the direct beam. So you are going to block this, and now you are going to project this onto your screen. So this is the entire thing is happening. So you can generate the this diffraction pattern also, which is going to satisfy that n lambda equal to 2d sin theta, that Bragg's law. And after that, if you want to image that, you can change the strength of the objective lens or the projector lens as per your accordance, and you can convert that. You can focus on any particular diffraction spot, and you can convert that to the image, knowing that, okay, which are those grain, which are the microstructure which is contributing toward this particular diffraction pattern. Now let me know, Prahlad sir, any doubt?
You see,
Yeah.
I think you got my query properly. Why diffraction spot cannot be called scattering spot? What I understand now, when electrons falls on the samples, it transmits through the samples, and scattering phenomena takes place.
Yep.
And out of those scattering things, when it is passing through the objective lens, those electrons which are meeting the requirement of n lambda is equal to 2 sine theta, they will be only diffracted, and those things only we are collecting as a diffraction spot.
Yep.
And other electrons which are scattered, they are going whatever area they are going, that is not our botheration. So those electrons which are getting the filling the requirement n lambda to the sine theta, those are getting diffracted, and this all the spot which we are calling as a diffracted beam, diffracted spot, all are meeting the requirement of n lambda is equal to 2d sine theta. Is that correct?
Yep.
That's all. Actually, nowhere in the professor has talked about this point. Then this question in my mind, I thought of let's get clarified. Thank you.
Yes, yeah. That. It was a very good question, and it's one of the most popular interview question you will see if you go to any. Let's say you are applying for a PhD, or if you are applying for a faculty position in any IIT or NIT. They will always ask you that what is the difference between the scattering and the diffraction. So the correct answer is that the diffraction is also a scattering, but is a special kind of scattering. For example, let's say your electron, incoming electron or incoming beam is also going to interact with the electrons of the material, right? In that case, what will happen? It will scatter somewhere. It will scatter to some region. Backscattered electron is also like it is a scattered. It changes its direction, so that is also there. But the diffraction is where the condition of the Black's law is being satisfied and you are getting the diffraction pattern. So, but that is also the scattered one. So the diffraction is the special case of the scattering. Sorry. Yes. So the diffraction is a very special case. So if you take the entire globe as a scattering, the smaller region can be called as the diffraction, because the random scattering is already there in the specimen. For example, the mass thickness contrast is always present in your image. So in that case, the scattering is always happening. So even though you are trying to, let's say, someone did the imaging using this particular diffracted beam, but still, it cannot be the image which you have obtained, the grain structure or microstructure which you have obtained. There also the mass thickness contrast is also going to be contribute. Okay, so this is how since the mass thickness contrast is coming due to the scattering itself, right? So the phenomena in the mass thickness contrast is not due to the diffraction, but it is due to the scattering. Okay, so this was the entire thing, and it was very good discussion. I liked it. Okay, guys, any doubt? Let me know. If not, we'll move ahead to the next question. Question number 6. Yeah, here it is. So, what is the primary function of the fluorescent screen in the TEM? To generate X-ray for chemical analysis, to convert electron signal into the visible light for the imaging. Very good, Prahlad. That's option B is the right answer. Yes, Uday. The option B is the one. It's the one which is going to convert the electron signal, which our eye cannot see them, to the visible light for imaging. Okay. So with that, question number 6 is over. Any doubt, guys? Let me know. Yeah, here. The question number 7. In TEM, the contrast formation on the fluorescent screen depend primarily on the wavelength of the incident electron, the number and the phase of the electron hitting, the temperature of the specimen, the magnetic field strength of the objective lens. Very good with that. It's option B. So it's a number of phase of electron. The number and the phase of electron. Okay. So more is the electron density, you will get more your image will be more brighter, your microstructure will be more brighter. Less electron, dark. Right. This is for the question number 7. Let's go ahead. Question number 8. Elastic scattering in TEM predominantly affect which property of the electron? Now elastic scattering we are talking about. Elastic scattering we know. The scattering can be contributed in the two part. One is that elastic and inelastic. Elastic is the one where the energy loss is not there, and inelastic is the one where energy loss is there. So elastic scattering in the TEM affect which property of the electron? Energy, wavelength, phase, or charge? What do you think? Is it going to change the, let's say elastic scattering is happening, is it due to the, is it going to change the energy of the energy of the beam, the scattered electron? No, the energy is going to conserve. Energy is same, wavelength will not change. What is going to change is the phase. The charge is not going to change, because what I put the electron and again what I am getting the is electron itself. The charge is remaining same. So again, so right, so it's a phase which is going to change. So phase, you mean we got right that again one can understand it from the perspective, okay, elastic scattering, okay, diffraction is happening. Diffraction is what? The phase change will occur. Phase of the beam, which property of the electron? Phase of the beam, the phase, this type of. So it can either move ahead, if it is integral multiple of the lambda, then we will get that, okay, it's a constructive interference. Okay, with that we've got the option C is the right answer. Let's move ahead to the next question, question number 9. Electron lost their energy during their trajectory through the material due to. Now electron is losing energy. Why? Inelastic scattering, elastic scattering, both, none of them. Very good, Prahlad, and very good. Yeah, Uday, Gitu, yes. Option A is the right answer. It's due to the inelastic scattering. And very good, Ahmed. That's good. Now we have to talk about the mass thickness contrast a little bit. Okay. Mass thickness contrast. So now consider the region in your specimen. Let us say this one is having the mass m1, this is having the mass m2. m1 is more than m2. Now when I'm talking about the mass, we are, okay, there is a question, during scattering energy is conserved. During scattering energy is conserved, the answer will be the no. During scattering energy is not conserved. During diffraction energy is conserved, that's yes. Right? And so scattering, we just now talk about that it can be elastic, it can be inelastic. So in inelastic scattering, we know that it's going to be the one, the energy will lose. Right? So the certain part of the energy will went to the maybe material or somewhere, like heat will be generated. So in that way we can lose the energy. Okay. Yeah. So now here, let's say m1 is greater than m2. Again, we are talking, when we are talking about those things, like when will I have a more mass? When the density of the particular material will be high. Higher density means highly close pack, right? Highly close pack. So let's say now again, let's come. This is the more, m1 is greater than m2. I pass the electron beam. So what is going to happen? Here, the atoms are densely packed. They have the density is more. In that case, what will happen? It will scatter more. So m1 is going to scatter more than the m2. So what we will see on the screen, that since if I'm seeing the direct beam, what I will observe that since m1 is scattering more, what I will see, it is the direct beam will be darker. And m2 is scattering less, it means that it will be brighter. Since it will scatter less, the direct beam will have the more intensity. Here, since scattering more, direct beam will have the less intensity. Okay, so this is about the mass. Similar thing we can say about the thickness also. Let us consider the specimen, something like this. Udaya, scattering energy does not remain conserved, but for the diffraction energy remain conserved. Is it true? Yes, it's true. This is how it is. Because the diffraction is we can say the elastic scattering. Okay, when we try to relate this particle nature and the wave nature together, we can say that, yeah, its diffraction is more or less elastic scattering. Okay, now let's talk about the mass thickness contrast. Sorry, now we talk about the mass, let's talk about the thickness part. So now let's say case 1 and case 2. In which case, I would like you guys to answer that, in which case the scattering will be more, in the case 1, or it will be more in the case 2. scattering, where it will scatter more. What do you think? The one or two? The one is having the more thickness. Again, we are talking about the TM, so the electron beam will pass through it. Very good with that. There's the first one. First one is going to scatter more compared to the second. So now, since it is going to scatter more, the first one, will it be brighter or will it be darker? Will it be brighter or will it be darker? It will scatter more, right? So that in the direct beam, we are not getting that, the intensity. So what it will be? Let's say, this is my specimen. Let's say I am the material one, the reason one I zoomed it over here. Now what is happening in the material one? It's scattering more. The scattering is more. So the direct beam is less. So what will happen? What will I get in the screen? Very less amount of intensity. Well, in the case 2, where the scattering is less, let's say it went through this, but the scattering is less. So the more of the direct beam is coming. So in that case, I will see that it should be the brighter. So the thickness is less, then it will be brighter. So here, in the case 2, here it will be brighter. Why it will be brighter? Because it will scatter less. Here it will be darker because it will more scatter. Right? I hope I'm clear. If any doubt in this, guys, please let me know. Okay. Since there is no doubt, let's move to the next. Let's move to the next concept. See. Consider the specimen. Let's consider this part. Okay, one more thing we consider that, okay, this is the geometry is something like this. So the one part is again thicker, another part is thinner. In the case 1, where it is thicker, in the case of thick one, what we observe that the direct beam is less, the scattered beam, they are more. In the case 2, where there is a thin, in that case, we are seeing that there is a more direct beam and the scattered beam is less. I was seeing the direct beam. I saw for the direct beam, in the case 1, the direct beam will be the darker because there is only very few signals are there. Here it will be brighter. Right? Now, I'm not, let's say, in another case, I'm not using the direct beam, I'm using the scattered beam. I am imaging this scattered beam. So now, if I'm not using the direct beam, if I'm using the diffracted or scattered beam, what here it will be? It will be darker or it will be brighter? The case 1. It will be brighter or it will be darker? What do you think, guys? Here it's scattered more. So now I'm seeing the scattered beam. If I move my detector from here to here, now what's going to happen? Will I see the more or will I see the less compared to this? Here the scattered beam is, since there is a more scattered beam and I'm seeing only the scattered beam, so here it will be the brighter. Here it will be the darker. In the direct beam it was brighter because why? The scattering was less. So now if I went to the screen and now I'm going to see the scattering only, scattered beam. Scattered beam is only, okay, there is very less, so I don't have much intensity, it will be darker. Here the scatter beam are the more, they are more in intensity, they are more in the number, they will be brighter, right? So it's all depend upon the perspective from where you are seeing it. So in the similar way, there is the this thing is there, like one is the we just not talk about the direct beam and the dark beam. Okay, so now let's talk about the dark field only. Now let's say, now these are these two cases which I'm telling you, that these are the just the way how you can say this. How you can say this, this is just the way. One thing is that, let us say in the direct beam, your beam was coming, it was interacting with your specimen and it was going. And you were also getting some diffracted or the scattered beam. What you did, you took the aperture and you blocked remaining all the things. You are only seeing the direct beam. In that case, you will get the bright field image. Now, if you want to see certain particular region where we don't want to see the brighter one, you want to see the darker one. Okay. Sorry, you want to see the scattered one. You don't want to see the direct beam, you want to see the scattered beam. In that case, what you will do? What you can do is that you can move your aperture from this location and you can keep it somewhere over here, where you are going to get the scattered beam. So this is, see, we can see instead of keeping the aperture here, we kept our aperture here. We just move the optical aperture. Now we are seeing the diffracted beam, or you can say the scattered. Now you are going to image with that. So this is the one way you can move your aperture. You can move the aperture. You can block the other things. There is one more way. You can tilt your specimen. You can bend the, like this one, right? It was like this. You can bend the entire thing. Let's say you want to keep your aperture as it is, the first one where it was, you want to keep it there itself. You don't want to change the aperture. In that case, what you will do? You can bend this entire geometry. You can make sure that the one which was coming onto this initially, let's say the one which you are imaging over here, now it will come along the optical axis. You kept your specimen, you kept the aperture position as it is. So now instead of the direct beam from the same location, the diffracted beam is passing. Just what you did, you rotated the specimen. Okay, so you can either rotate this entire thing, or you can shift this thing. This is the entire thing. So now in this case, what is happening, that it's the off axis dark field, it's the on axis dark field, it's on the axis, it's the off the axis. Okay, good. It's off axis because it's not along the axis, it's not along the direct beam axis. Whenever we talk about the axis, we always talk about the direct beam axis. Well, this one is again the on the axis, like the along the focal length of the objective lens. Okay guys, now based on the thing that we have discussed, let's try to answer this question. Which of the following region in TEM image would appear darker in the bright field mode? See, we are talking the bright field mode. So whatever the concept that we have discussed till now, first we discussed about the bright field mode, mass thickness contrast. We discussed that in the bright field mode, which one will appear brighter, which one will appear darker. Then after that, we discussed about the dark field mode. So now we'll try to solve questions based on both the concept. So now, which of the following region in the TEM image would appear darkest in the bright field mode? So a thick, okay, Ahmed is telling it's a thick, high atomic number region. Very good. So the one in the bright field mode, the darker one will be the one which will scatter more. Okay, so it's option B is the right answer. Very good, guys. So it's clear that we are getting. Now, if I ask you which one will appear brighter, what would be the right answer in that case? If instead of darker, very good, Ahmed. Sorry, very good, yeah. Uday, Ahmed, yeah, everyone. The option A is the right answer in that case, right? Yeah. So let's move ahead to the next question, question number 11. Now we are talking about the dark field. In dark field TEM imaging, point to be noted that we are talking about the dark field. The image is formed using direct beam, diffracted beam, excluding the direct beam, backscattered electron, secondary electron. What is the right answer over here? Prahlad and yeah, Uday. Yeah, very good. It's a diffracted beam we are going to use, right? In the case of dark field. Very good, guys. So now, like in this case, what we did is instead of direct beam, we are using the diffracted beam. Or yeah, that's the one. Option B is the right answer. Let's move ahead. Next question. Now, little bit of thinking we have to just do. What will be the contrast generated due to the atomic number effect for the TM bright field image of an alloy containing magnesium and the zinc? So we have magnesium, we have zinc, and we are talking about the bright field mode that we are seeing the direct one. Zinc will appear dark. Okay, Uday is telling that the zinc will appear dark than the magnesium. The answer is right. It's very good. Now, what is the point of difference in between the zinc and this magnesium? The thing is that they are differed by the atomic number. The atomic number of zinc, I think it's a 30, and Mg is 12. Okay, so this is more. So now zinc atomic number is more, it will scatter more. So in the direct beam, you will see the less number of beam, less number of intensity. So this will appear darker. This will appear brighter. Right? So this was the thing. Okay, so the right answer is option B. Okay guys, if any doubt, guys, please let me know. Okay, now let's move to the next question, question number 13. Yeah, the first one. In bright field TM, thicker region of the specimen appear brighter than the thinner region. True or false? They are telling that the thicker will appear brighter. Very good, Prahlad. It's false. It's the other way around, right? The thinner region will be brighter and thicker region will be dark. Very good. Yes, Sudha, yeah. So now let's go to the next one. The dark field imaging use the direct beam to form the image. True or false? It's a false again. So here, it's a false. We are going to use the diffracted beam. Very good. Yes. And the last one. Elastic scattering change the electron energy and the wavelength. Elastic scattering. False, right? It's not going to do that. The energy is going to be same. There will be this. Since the energy is same, the wavelength will be same. With that, we have solved the question number 13. Let's move to the next question. It's a mass pair type. Guys, please go through this. The first one is the mass thickness contrast. What do you think? Which one will be the right answer? So, for the mass thickness contrast, diffracted beam form the image, difference in the specimen thickness and density, high Z material, scatter more, interference due to the electron phase shift. Very good. Yes, it's the option B. Mass thickness is the difference in the specimen due to the thickness and the density. Right? Very good. This is what we have seen in the mass thickness contrast. Atomic number contrast. What will be the right answer? C. Very good. So in this case, it will be the C. Higher Z material, scatter more. Okay. Phase contrast. It will be the option D, right? The interference due to the electron phase shift. The right answer is D. And the bright field image and the dark field image. Bright field image, which one will be this one? Yes, Prahlad, it's option E. So here, it will be the direct beam from the image. Dark field, we already know that. The only option left is the option A. Okay, so with that, we have solved this question number 14. Okay, let's move ahead. If there's no doubt, then let's move ahead to the next question. Question number, okay, before we go ahead, let's discuss this concept. So now here in the TEM, this was the incident beam, this was the this is the direct beam. So direct beam we call it to be the bright field detector. Now there are the various detector. There is a detector, annular dark field detector. So we are not going to with this detector we are not going see. First of all, annular means that it's a something like this shape, and it will be something like this. This is hollow, so the detector is this much. So now it is it will capture only the direct beam will not go through it. Only the beam which are at certain angle will go. So it will capture the image. It will capture the information only from a certain particular angle range, solid angle range. Okay. Now hard F will capture even more angular, like it's known as hard F is known for the high angle. This HA, initial HA is high angle, annular dark field again, annular dark field. Since we are only going to capture the dark field image with this, and since it's a annular, and now here we are going to capture the high angle one, so we call it the hard F detector. So now hard F detector, see, hard F detector what is doing that it's only capturing RF detector is only capturing the signal having the Z contrast. That is atomic number contrast, right? More or less one can say that it's behave like the BSC detector in the SEM. Now, annular dark field, it has the it captures the mix information. It captures the information of the Z contrast plus it captures the information of the mass thickness contrast. Right? So now, so what is happening that the scattering which is happening, from the mass thickness contrast will not go to the very high angle where the hard wave is placed. So there we are not able to see any mass thickness contrast. There we will only see the Z contrast. So if you want to resolve, if you saw your image in the annular dark field and you are not convinced yet that okay, whether it's coming from the Z contrast or it's coming from mass thickness contrast, then you can go to the hard F. In that particular detector, you will only see the Z contrast in that. There won't be any mass thickness contrast. Okay. One thing is that a thickness contrast will be there little bit. The thickness contrast will be there because let's say your one grain having the higher Z is overlapping with another grain having the higher Z. Both are having let's say same Z. Now if you project this particular region will appear more brighter compared to this. This two also will be brighter, but this one will be even more brighter because we know in the TEM what we are getting, the information we are getting, the projected information. It's throughout the thickness, throughout the specimen, what is happening. So thickness contrast will be there. The mass contrast will not be there. Okay guys, so in this entire discussion, if there is any doubt, let me know. If not, let's try to solve few questions. Hard F, the first one. Hard F mode in the TEM provide information about, what do you think? Among this, which one is the right answer? Option D is the right answer, right? Very good. It will provide the atomic number contrast. Very good, guys. So this was the question number 50. Let's solve this itself. A. Dark field imaging reverses the contrast seen in the bright field mode. What do you think? It's a true or false? Dark field imaging. We discussed just before the last discussion. Dark field. It's true. Very good. So whatever was appearing brighter in the direct beam will appear darker in the dark field. Whatever was appearing dark in the direct beam, will reappear brighter here. It will just reverse the effect. Now, the second one. Diffraction contrast can be fully explained by the mass thickness variation. Is the diffraction contrast is coming from the mass thickness variation? What is the answer for this? It's a false, right, Prahlad? So here, it's a false one. So the diffraction contrast is not coming by the mass thickness. Okay, it's coming due to the diffraction which is happening. Mass thickness is just a random scattering. Now, the third one, hard F. Hard F imaging use the low angle scattered electron for the atomic number contrast. What do you think? It's a false. Very good. The right will be that it's used the high angle scattered one. Okay. Option C. Now the last one. The polycrystalline material always show the uniform diffraction contrast across all the grain. It will depend upon their orientation, right? And the answer is false. It will depend upon the orientation. In what orientation the grain is there. Very good. Okay, now let's move to the next question, question number 17. It says that in bright field TM, okay, focus here that it's a bright field. Bright field TM, the grain satisfying the diffraction condition appear. The plane which satisfies the diffraction condition. Since it satisfies the diffraction condition, it's not going to come under the bright field. It will scatter somewhere else. So, what do you think about that? So it will appear brighter, darker, unchanged, or with diffraction ring. So the brighter field, the bright field in bright field TM, the grain which satisfies the diffraction contrast. Okay, what will be the right answer? With diffraction ring, see, diffraction ring, those things that diffraction pattern, you will not get in the bright field. When we talk about the bright field, those things, this term itself is highlighting that we are talking about the image. We are talking about the microstructure. So here the diffraction pattern will not be recorded itself. Okay. Here we are not talking about the diffraction pattern. This thing we are not talking. So in the bright field, what we will get the image only. So now let's say you had the microstructure. This was the microstructure. And a particular grain, let's say this grain. It satisfied the Bragg condition, it satisfied the diffraction condition. So now what will happen that since it satisfies it's the intensity, this grain is going to diffract instead of going straight forward with the direct beam, it will diffract it somewhere else. Now since it's going to diffract it somewhere else, in the bright field what we'll see, it will be the darker. In the bright field you will see it's a darker. While on the another hand, if you see for the dark field, so our right answer is the diffraction beam is darker due to the electron loss from the direct beam. Now, instead of bright field, if you say in the dark field, how it will look like? The microstructure will look just the reverse. Now the grain, this grain will be the only grain which will be visible and it will be brighter. Remaining all the things will be darker. This all will be darker. it depends upon what you are seeing, from what perspective you are seeing. If you are seeing the diffracted beam, if you are seeing the diffracted beam, if you are seeing the direct beam, they both will give the opposite effect. Okay, so is it clear? Is there any confusion? Let me know. Okay, since there is no doubt, very good. The right answer here is option B. Let's move ahead to the next question, question number 18. We are left with few questions only, not much. The 18, the hard F. Hard F. Imaging is particularly sensitive to mass thickness, atomic number, magnetic property, beam damage. Very good with that. It's option B. Yes, Gitu, yeah, the right answer is option B. Yeah, is better. So with that, we have solved this question also. So this was the most important thing that hard F can do. Okay, we'll keep this thing in mind. Now, the question number 19. It's little interesting. The primary difference between the annular dark field and the high angle annular dark field detector is ADF detector detect backscattered electron, hard F detect the secondary electron. Hard F cover a high solid angle for the high angle scattering. So what do you think? Hard ADF is used for only in SCM. Hard F cannot resolve atomic column. See, we know that if ADF annular dark field is covering this much angle, our hard F is even at the higher angle. It will cover the solid angle which is over here. So let's say this is our direct beam which was coming. So the annular dark field only cover this much, while the hard F will cover more angle. So it will cover a higher solid angle. Now we are talking about the cone. It is higher. It will cover the higher solid angle for high angle scattering. Right? Yeah, very good with that. Yes. So the right answer is here is option B. Okay. Any doubt, guys? Let me know. Okay. Now let's see. Yeah, only 3 questions are left. Let's try to solve them. A. What about the option A? See, backscattered electron. The term backscattered comes in the SEM. For the backscattered electron, you should place your detector above the specimen. While we are talking in the transmission geometry, here we are hard F is somewhere over here, and ADF is somewhere over here. Right. So this is the incorrect one. We are not covering the backscattered electron. Okay. Okay. Now this one. A crystal is irradiated with the X-ray of wavelength lambda 1.54 angstrom or 0.154 nanometer. The first order Bragg-Shaw reflection equal to 1 is observed at the angle 2 theta equal to 60. Calculate the distance between the atomic plane. Okay, so our D is missing. We know the Bragg's law, since they are satisfied, it is tell that the Bragg's law are satisfied, m lambda equal to 2d sin theta we can apply. See, sometimes students make a mistake. They convert this sin theta directly to the theta. One should check what is the angle. Angle is 60. You cannot do that. If the angle is smaller than 1 or somewhere near to the 1 or 2 degree, in that case you do. So now, the order of reflection we know that it's the 1 multiplied by the wavelength is given 0.154. 2 multiplied by the d multiplied by sine of theta. That is nothing but a 30. 2 theta is 60, sine theta, so theta is 30. So we can solve this. Sine 30 is what? 1 by 2. So we can 1 by 2 and 2 will be cancelled out. So d spacing will be given by 1 multiplied by 0.154. So we can see that the d spacing is nothing but nanometer. So I hope it's clear. So this is how we have to solve the questions. Okay, just substitute the value, whatever it's given, and you can do it. Focus on the what is the order of reflection is. They told it's the first order. Easy question it was. Let's move ahead to the next question. Question number 21. Uh-oh, it's the same repeated. I forgot to remove it. Yes, guys, any doubt? Okay, let's move ahead. What is the zone axis for this and this particular plane? We know zone axis is the axis which is perpendicular to the whatever the set of the plane is given to us. Okay, let's say yeah, so it will be perpendicular to this particular planes. So now since it will be perpendicular to that and we want to find the zone axis, what do? You just do the cross product of them. You will find a similar question in the assignment. So all you have to do is the cross product over here. So we can see that 1 minus 3, it will be the minus 2. Minus 3 minus 1, it will be minus of 4. In this case, 3 minus of minus 3, that is plus 3. So it will be 6. So now again you can normalize it. You can say that it is the minus 1, minus 2 and 3. So I will write 1 bar, 2 bar, 3 bar. If in the question it's also given that 1, 2 and 3 bar, this also is the correct one. So both are correct. Okay. So this is how you have to find the zone axis. Okay. So usually we try to align our, yes, Uday, any doubt? Okay. So usually we try to align. Praladishan, can you please explain? Okay, yeah, very good. Okay, guys, let's say this is my specimen surface. But if you don't have any doubt, like you are not audible, I think some noise is there. Like I'm not able to hear you. Uh, since there is seems like there is a network issue, you can always post your question in that case in the chat box. Okay. So now let's say our specimen is a single crystal. They will have certain particular orientation. Atomic plane will have certain orientation, right? So, for example, let's talk a particular case. Let's say we are talking about the cube. Better I take the bigger page. Let us say this is the crystal. I made a blunder. I should have explained some other concept over there. Now consider that this is one plane, this plane. Right? Yes, brother, we'll come to that, how to calculate that. Now, consider this also. This plane. How do we characterize a plane? We characterize the plane by their direction, right? The direction of the plane will be always perpendicular to them. So the direction of this red one, it's along this, and the direction of the blue one, it's along this. So what will be their zone axis? It will be the cross product of these two things. It will be along this. The final zone axis will be along this. It is a cross product. So this is a common axis. This is the common axis between this plane. Also, you can also say that, what about if you say that, okay, let's say took this particular plane. So this particular plane, this particular direction is again perpendicular to this particular directions. It's a normal to this direction. Okay. So so 1 is a zone axis. This is a zone axis for this particular plane. This particular plane is nothing but the red one. The red plane is 100. This blue plane is 010. What about this particular one? Which plane is it? Can anyone tell me which plane is it? How do we find those things? Like in that case, what I will do, I will shift my origin. I will shift my origin over here. And what I will say, okay, this is my x, this is my y, and this is my z. To z, it's not intersecting. To the y, it's intersecting at 1. To the x, it's intersecting at 1 bar. So this is a plane. So the zone axis is the one, it's the common axis between all these planes. Now if you do cross product of this particular plane, or let's say, or this plane, 1 bar, 1 0, their cross product, like cross product of any two of them, will result to this. So for any even given set of the planes, you can do the cross product and you can find their zone axis. Okay, so the zone axis is the common axis between the set of the planes. Okay, so here I was drawing the long things. The perpendicular to the plane, it means that it should be perpendicular to the direction of the plane. Okay, so for this particular plane, the direction is this. Now, the Prahlad had asked that how to find the zone axis. So again, if you are given with the planes, all you have to do, you have to find their cross product. For example, this was a plane 1, this is a plane 2. When I did the cross product, I found the z. So z is equal to the 1 cross 2. Right? Is it clear, guys? Let me know. Is that the question, Prahlad, which you have asked? Yep, great. So you will find. Yeah. Yes, Uday. Any doubt? Okay. So you can find the zone axis like this, and also we will find the similar questions in the class assignment. And okay, Uday Kumar has left. Okay. Okay, guys. So with that, I think if you have any doubt in the entire discussion that we have made today, let me know. If not, we'll move ahead. We'll wind up the 246 how to calculate. Ahmed, 46. I not got. Can you unmute yourself and you can interact with me? Like what question you are talking about?
The last calculation, class calculation. Really, I don't know what class we need to. Example 1 minus 3 minus 2. That I understood.
Okay. Mhm.
Then this 4, how it is came, really, I don't know. And the 6 and 5, I don't know how it is
Okay.
fixed.
Yeah, I'll tell you. Let's have a discussion on that. This way. But I should use something which is, yeah, this one is good. So 1, 1, 1 minus 3, 3, 1. This were the two planes given to us, and we want to find a zone axis. The zone axis is again it's a direction. So I, J, K. Now we have to do the cross product of this. So let's write them like this in this way. So now how do we do the cross product? For the I components, we can multiply this 1 into 1, 1 minus of this into this, that is 3 times I. Plus for the j, we can do like this, minus 3 multiplied by 1, that is minus of 3, minus of this, that is 1 into 1. This is j. Plus, let's talk about the k. 1 into 1, that is 3, minus of the next product, that is minus 3 into 1, that is minus 3. This will be the k component. So now what we can say, that it will be the minus of 2i and the minus of 4j, and it will be the plus of this minus minus will be plus, it will be 6 of k. And so this is how we can say that it will be the minus 2, minus 4 and 6. And we can again normalize 1, 2 and minus of 3. Is it clear now, Ahmed?
Yeah, it's clear, but with the graphs, what is the general formula? You did something crass, but is there anything the formula is there? Which way we need to do
Yeah.
crass?
Formula is this itself. Let's say we are talking about the plane h1, k1, l1, and h2, k2, l2. And the entire method which we did itself is a formula I, j, k, and let's say instead of the number, this time I will put the h1, k1, l1, h2, k2, l2. Okay, so now it is having some, let's say, z. So now what we can say, that it will be like the answer which we will get, which I will get, is h1 into l2, sorry, k1 into l2 minus k2 into l1. This will be the I component. Then again we can say, right, what about j component? We can say h2 multiplied by the l1 minus of h1 multiplied by the l2. This is j component. And again we can write the k component as h1 multiplied by the k2 minus of h2 multiplied by the k1. Okay, so if you have to find the h component, it will like the hkl, if you say in that way. So the h component will be this part, h1 l2, k1 l2 minus k2 l1. K part will be the, right, let's say h2 l1 minus h1 l2, and the l part will be like h1 k2 minus h2 k1. This is how you can do. This is a formula which you can use, but I won't suggest you to mug up this thing. It's very confusing. At times you can forget. Better to use.
Just 1 minute. See, you have made K1 L2 minus K2 L1, correct? I. Then next one is there H2. I think it will be H1 L2 minus H2 L1.
Actually, when we do cross product now, in this case, for the second one, the sign will reverse, right? This one, it will have the plus sign. It's a mathematics, like 1 minus
I understand.
right?
Okay.
So if I incorporate this minus itself, so instead of going from this direction, I have to go in this direction. I will go opposite. Or if we want to do the way you said, in that case we have to add the minus sign at the initially. So it's just a basic mathematics.
Yeah, I understand. Thank you.
Yeah, great. Yes, guys. Any other doubt in the entire discussion that we have made?
Sir,
Yeah, there.
sir, I have a question on current assignments. Could you please confirm week 4 assignment question number 15? 2 theta value either 300 or 30 degree. Last session we have discussed 60 degree, then the theta will be 30. Here they are giving 300.
This one is 30.
30 or 300? 30.
30 degree, yeah.
Okay, fine. Sir, one more thing, we are facing issue on the problematic. Every problem session, we are only able to type the number only. We could not able to type the letters like unit. Like it's for example, we are typing in a wavelength, nanometer, tachometer, or picometer. We cannot able to type. So we are solving the problem. We could not able to mention the unit, so we unable to get the mark.
Yes, Uday. I agree with you. The thing is that the one who made the question, he should have specified, he or she should have specified in what unit we have to write the answer. In the case, since we have already posted, I think in the doubt solving forum, that Q&A forum, So we are going to provide the grace mark. I will very soon. I will write a mail to NPTEL team. So for that case, since your answer is right, just the unit that is also the mistake is from the technical team side. So you will be awarded with the mark. So no need to worry about that. And from the next time onwards, we will be a little careful. And for this question also, we can say that the unit is not provided. In what unit we have to write the what we can say
That what you
D,
need, sir.
yeah, D spacing, right? So for a timing, I would suggest you to write in the Armstrong. If it is not,
Armstrong.
if they give that in the nanometer, then I'll try to talk with them and the mark will be provided.
So you are telling that you go with Armstrong, right?
Yeah, go ahead with
Okay.
that. Yeah,
Okay. The theta is so 2 theta is 30 degree and the unit is Armstrong, right?
yeah, yeah. Here you can write the unit in Armstrong, the answer for the D
Okay.
spacing.
Okay, sir. Okay. Then week number 3, question number 8, the Planck constant value given 10 power minus 34. The actual value is 10 power minus 39, right? That is what the lecture
Planck's constant.
is, sir.
Actual value is how much you are telling that?
10 power minus 34, right?
Uh, let's see the unit. Let's see the unit of the Planck constant that has been provided.
Sir, you can go with week 3, question number 8.
Question number 8 and 9, same thing is there. 9 also the same thing. What in 9 also what equation it was discussed, I think 1.67, but in solution it is not discussed on that.
Yep. So I think that is also for question number 8 and question number 9. Very soon, maybe by today itself, I'm going to write the mail to the NPTEL team. So for that, we'll try to provide the grace mark. I'll just discuss with the professor.
Sir,
Yes,
sir, could you please award these two 8 and 9 reward the marks? It will be fine, sir, because the unit is not there and the question also mistaken, I think.
Yeah.
I also get 0 marks on 8 and 9.
Sir, I write it in the discussion forum also. And one more thing, sir. Question number 9, week number 3, question number 9. In the problematic session, what we are discussed,
Yep.
the formula will be 0.67. I repeat the question again.
Correct.
Yeah. I went through that.
Just
They
a
neglected
minute.
that.
Just a minute. Okay, question number 12. What we were discussed in the online session last class. This is not the current assignment. It's a online session question. Question number 12. Calculate the optimal resolution and the aperture semi-angle for lambda equal to 1.5 picometer and the CS value will be 1 micrometer. Sorry, mm. So you. Sir, it's a online. We were discussed, sir. We were discussed.
Yep. I remember that. And also it's
So
there in the lecture.
Yes, sir. You told that the formula is 0.67 into lambda by CS whole power 1/4. That is what you told, sir.
Yeah. I remember that.
See, same thing, same formula we applied here. The question number current assignment, question number 9, we applied here. The answer will be yes, sir. The answer will be 0.047 something. But here how they are calculated 7 or 7.5, they skip 0.67. They are simply go with lambda by CS whole power 1/4. Then they will get 7 into 10 power minus 3, I think.
Yeah.
So they take it rounded value as a 7. They skip 0.67.
Yep. Yeah.
So
yes,
sir.
what we'll do is that we'll try for question number 8 and question number 9, week 3 assignment.
Yes, sir.
We are
Yes,
going
sir.
to write a mail very soon, and we'll try to sort out this entire thing. And like if I will try my best that the grace marks should be provided because you have followed that procedure. And the mistake is
Okay,
from the technical team side who not wrote the unit, and the formula which
Yes,
is
sir.
used is wrong one.
Thank you, sir. Sir, question number 8, question also wrong. 10 power minus 13, I think. H equal to 6.63 into 10 power minus 39, I think. You can once again check.
It's a 34.
Then 34. Here 34, sir, but the lecture size at 10 power minus 39.
In which lecture? Is it with
So,
me for that dot solving session, or you are talking about that professor lecture?
sir, lecture material in that video, I think.
Okay,
Okay, sir.
okay. Anyway,
Okay, sir. You can check once again, and then if it is possible, kindly reward the marks, sir, 8 and 9.
yeah, sure.
And one more thing, you have to kindly enable the unit option, or you else you have to mention the answer should be in what unit in that question, or else you can enable the unit option. We can type, sir.
Sure, Uday, yeah. We'll talk with the technical team for this, and very soon we'll update you on that Q&A forum. And
Yes, sir.
yeah, everyone, whatever the doubt you are facing, you can always put it on the Q&A forum. So it is not only we are the one who is reviewing, even the NPTEL team is also the reviewing that. So
Yes,
based
sir.
on
Yes, sir.
that,
Yes,
action will be taken. So
yes,
no
sir.
need
Yes,
to worry
sir.
about that.
Thank you, sir. I write discussion forum also, sir. Mail, sir.
Sure, sir. Yeah. Okay, Uday.
Okay. Thank you so much, sir.
Yeah. Okay, guys. Any doubt?
I have only one concern here.
Yeah.
In the future, whatever the mathematical questions are coming, the answer is coming. Rest of the other non-mathematical give very clear explanation, but mathematical calculation, it's not giving any detailed steps on it. There is a people coming with what is that, strong mathematical skill and low mathematical skill. Also, the peoples are joined in this course. So that answer should be given that clear steps with what the formula is involved and what is the multiplication or division is involved to reach that answer. That explanation needs to be clubbed because we came to until 4, but each assignment has the mathematical calculation. But I have seen that one. The only answer is displaying, but rest of the other line item kind of question, there is a explanation is always there.
Okay.
This needs added. That's it.
Okay, so yeah, we'll try to update those solution. We'll talk with the professor, and I would suggest you just one thing that whatever that thing you have mentioned, if it will be very good, like if you put it on the Q&A forum, that so that I can take that as a reference and I can discuss with the professor that okay, these are the doubt, these are the problem the students or learners are facing. Okay,
Yeah, sure. I will do that.
yeah, sure. Thank you, Amber. Uh, any other doubt, guys? Okay, since there is no doubt, I think we can wind up today's session. I hope you have learned, and we can meet in the upcoming class next time, next week, same date and same day and same time, 3 p.m. Okay, guys, bye bye. Take care.